Okay, good afternoon. Our speaker today is Pierluigi Rinaldi, sorry, who took the master here in Bologna working with Professor Cimatti and then moved to the University of Captain in Groningen for the PhD. He's an expert on extragalactic, or is becoming an expert in extragalactic observation. He's already involved with JWST, simulations for the future, and the analysis of HST. And today will tell us about analyzing the starburst sequence beyond redshift 3. Please, stage is yours.
Hi everyone, thanks for having me here. Today I will talk about our very recent findings about the starburst main sequence bimodality at redshift greater than 3. But before doing that, I will give you a very brief background behind this study. As you may know, over the past decades, galaxy surveys proved constrain much better the theory behind galaxy formation and evolution. In particular, many correlation between some parameters useful to describe galaxy evolution and formation and evolution have constrained, but among them, the relation between star formation rate and stellar mass plane became extremely important because that relation suggests us, gives us constraint on the process of gas conversion into stars, the so-called stellar mass assembly. All these surveys over the past decades helped us to constrain this relation. As you can see here in this picture, we have the star formation rate stellar mass plane, and we have this the so-called main sequence of galaxies, which is a linear relation in the log-log plane. And this kind of relation is usually parameterized as a power law, as you can see here. And the slope of this relation usually ranges between 0.6 and 1, as found out by Eagle and collaborator 2014. However, in the star formation rate stellar mass plane, we can also find other kind of galaxies, which are this is the relation, the observed relation in the star formation rate stellar mass plane. As you can see here, the majority of galaxies, the so-called main sequence galaxies, lay on this linear relation, this log-log plane. And this relation basically is telling us that these galaxies grow up over cosmic time in a very self-similar way, catching all the cold gas from the intergalactic medium, the so-called cold accretion mode of star formation. As I told you before, in the star formation rate stellar mass plane, other kind of galaxies have been observed. We have the passive galaxies, which are characterized by an instantaneous star formation rate, completely negligible if compared to the main sequence galaxies. And above the main sequence of galaxies, we also find the so-called starburst galaxies, which are characterized by, given a fixed stellar mass, they are characterized by a very huge star formation rate. However, in the last 10 years, other properties have been observed in the star formation rate stellar mass plane. Firstly, Rodriguez and collaborator at redshift between 1.5 and 2.5 have demonstrated that starburst galaxies account only for 2% of the total sample they studied in that range of redshift. At the same time, these kind of galaxies account only for 10% of the total star formation rate density. So basically, they demonstrated that the presence of this kind of galaxies is completely negligible in the context of cosmic star formation rate density. But Caput and collaborator in 2017 have demonstrated that at higher redshift, in this case between 4 and 5, starburst galaxies are very common at this redshift, and moreover, they also demonstrated that at this redshift, a sort of bimodality between starburst and main sequence arises. So in this work, we wanted to study this kind of bimodality, and in particular, we wanted to catch the starburst galaxy, especially the low mass ones. And to do that, today we know that it really depends on which kind of cosmic time we want to probe. Today we know that if we study low redshift galaxies, we only need to exploit deep fields, as did by Bogart and collaborator 2018, where they are able to trace star formation down to 10 to the 7 solar masses at redshift between 0.1 and 0.9. But the more we go to high redshift, the more we need to combine deep fields and gravitational lensing, as did by Karman and collaborator 2017. In this case, as you can see, at redshift greater than 3, they studied a sample of lensed diamond alpha emitter galaxies, and they were able to trace star formation down to 10 to the 6 solar masses. So here we are. We decided, as I told you before, to study the star formation rate stellar mass plane, in particular to catch the starburst galaxies, the very high redshift starburst galaxies. And to do that, we needed to combine very deep observation, as did by the Hubble Frontier Fields program, and the gravitational lensing effect. In this case, we only studied 3 out of 6 galaxy clusters observed by the Hubble Frontier Fields program. In this case, I show you Max J0416, Hubble 370, and Hubble 2744. We had photometric information in 7 different bands, from the ACS camera and wide field camera 3 up to 1.6 micron. And basically, we studied a sample of lensed diamond alpha emitter galaxies at redshift between 2.8 and 6.5. Lyman alpha emitter galaxies are very young star-forming galaxies characterized by this prominent Lyman alpha emission line, which is useful in the context of cosmology at very high redshift. And these galaxies were confirmed by the spectroscope. The redshift of this galaxy is confirmed by spectroscopic observation taken by MUSE. So then we adopted Sextractor to extract the photometric information. In this case, we adopted the hot extraction mode as proposed by Galama and collaborator. And once we had their photometric information plus the spectroscopic redshift, we decided to infer their stellar properties such as stellar mass, color excess, ages, and so on. However, to avoid to be model dependent in the star formation rate stellar mass plane, we decided to infer the star formation rates directly from the observed UV fluxes, considering the Kennicutt relation. Here in this slide, I show you the first results we obtained. On the left, you can see the star formation rate stellar mass plane. On the right side, you can see the same thing, but this time from another point of view, which is the specific star formation rate, which is the ratio between the star formation rate and the stellar mass. I show you in yellow the starburst cloud as proposed by Caputi collaborator, where the starburst galaxies are all those galaxies with the specific star formation rate greater than 10 to the minus 7.6. And in blue, I show you the evolution of Spiegel main sequence prescription at redshift between 3 and 6.5. As you can see here, we are able to trace star formation down to 10 to the 0.5, 10 to up to 5.5 solar masses. We also found out that the majority of our sample is located in the starburst cloud, as defined by Caputi and collaborator. And as you can see here, the more we go down to very low stellar masses, the more the main sequence galaxies are very different to catch. And this is probably due to a selection effect that prevent any detection by MUSE observation. So once we understood that we were able to study star formation, to trace star formation over 5 decades in stellar mass, we decided to enlarge our sample. And to do so, we considered the SMAVS galaxies. SMAVS is a survey in the cosmos field over 0.66 square degree. And in the survey, we can study galaxy evolution over a wide redshift range from 0 to 7, if I'm not wrong. And in this case, we only consider all the star-forming galaxies between redshift 2.8 and 6.5. So our sample now is characterized by more than 20,000 galaxies. So we decided to split our study in 3 redshift range, from 2.8 to 4, from 4 to 5, and from 5 to 6.5. Again, here I show you the starburst cloud as proposed by Caputi and collaborator. The brown points refer to SMAVS galaxy. So As I told you before, Caputa and collaborator 2017 demonstrated that between Redshift 4 and Redshift 5, a sort of bimodality arises in this star formation ray stellar mass plane. So we decided to see if this bimodality applies to the whole redshift range we studied here. And as you can see on the right side, we consider the specific star formation rate distribution for the free redshift bin we analyzed. This plot is color coded by main sequence, the star formation valley, which is the region in between the main sequence starbust, and in the blue you can see the starbust zone. And as you can see here, we are able to find this kind of bimodality in the free redshift range, and we decided to compare our result to what Caputa and collaborator found back in 2017. As you can see here, we found the same result, but the most important thing is that this bimodality exists, but it doesn't depend on which star formation rate we decide to consider, because in this study, we infer the star formation rate from the observed UV fluxes, but in Caputa and collaborator, they infer the star formation rate directly from the H alpha excess. So two different methods gives us the same bimodality in the star formation rate stellar mass plane at higher redshift. So once we understood that in the star formation rate stellar mass plane, we can split galaxies in starburst and main sequence galaxies, we decided to make a linear regression separately for all this population in each redshift bin we analyzed here. And as you can see here, I show you the best fitting for each population in the star formation rate stellar mass plane for each redshift. And for reference, I also show you the evolution of main sequence prescription by Spiegel and Santini from redshift 3 to 6 and to 6.5. However, this comparison must be done with care, because compared to previous literature, in this work we applied a net separation between starburst and main sequence galaxies. And in the past literature, this net separation is, it didn't consider, they didn't consider at all this kind of separation. So as you can see here, the literature falls in between our best fit. So any conclusion here must be done with care. So we need to understand if can we apply this separation also in the past literature and see what happens. Then we ask ourselves, what is the fraction of starburst and main sequence galaxies in each redshift bin? But before showing you the results we obtained, I want to stress the fact that even if we look at the star formation rate stellar mass plane, but this time from another point of view, which is the 2D distribution, we are able to see these two different bulk of star formation. The first one located in the starburst cloud, and the second one located on the main sequence of galaxy. So this bimodality even is clear even if we look at this kind of plots. So as I told you before, we estimated the fraction of starburst and main sequence galaxies in each redshift bin. Here I show you on the left the star formation rate distribution color coded for starburst, main sequence, star formation valley galaxy. In the middle, you can find pie charts referring to the total amount of each kind of galaxies we analyzed in this work. And as you can see here, from redshift 2.8 to redshift 6.5, 40% of the total galaxies are located in the starburst cloud, which is an amount much bigger if compared to what Rodriguez and collaborator found at redshift between 1.5 and 2.5. But if we look at the total star formation rate budget, which is the total amount of star formation located in each kind of galaxies, we can see that 60–90% of the total star formation rate is located in the starburst cloud, which means that maybe the starburst galaxies were very common at high redshifts, and maybe the starburst mode of star formation was dominant at high redshift. So perhaps starburst galaxies could have played an important role in the cosmic star formation history. Moreover, we also noticed that all the low stellar mass starbursts with stellar mass lower than 10 to the 8.5 solar masses have ages comparable to the typical time scales of the starburst phenomenon. Then we estimate the star formation, the cosmic star formation rate density. And to do that, I forgot to tell you that for this kind of analysis, we only consider all those galaxies with the stellar masses greater than 10 to the 9 solar masses to be mass complete, even in the highest redshift beam here. So we estimate the star formation rate density, but to do so, we only consider the mass galaxies in this case, because considering the lengthy diagonal emitter galaxy could introduce large uncertainties in during the estimation of star formation rate density, but we estimated that the impact of these galaxies on the star formation rate density is completely negligible, up to 2%. So here I show you the star formation, the cosmic star formation rate density. As you can see here in red, our data are in good agreement with the literature. Here I show you the past literature with the data from UV plus infrared, also with the sub millimeter. I also show you here the comparison with the theory, with the Maddow and Dickinson 2014, and with the Lustris TNG simulation from PLP 2018. Then we ask ourselves, what happens if we compare our observation, our results, with one of the most present simulation that we can find in the market? Here I show you in this study we adopted the Lustris TNG, and in particular for this work we only consider TNG 50. I want to stress the fact that SMAPS survey, which is the sample that dominates our study, covers only 0.66 square degree of the cosmos field. And so the TNG 50 is much bigger than the Comovian volume proved by SMAPS. And we also, and moreover, we decided to consider TNG 50 because it's compared to TNG 100 and TNG 300, it is characterized by details even at small scale. So we compared our result with the Lustris galaxies, and here I show you the star formation rate stellar mass plane, where I plot the Lustris galaxies in each redshift beam, and the contour plot refers to all the sample we analyzed here, so the SMAP sample plus the lens diagonal emitter galaxies. And as you can see here, Lustris TNG seems not able to reproduce starburst galaxies at all. So to be sure about our findings, we wanted to estimate the specific star formation rate distribution also for the Lustris galaxies. And here, as you can see on the right side, comparing our observation with the Lustris TNG 50 in the same redshift beam, so from 3 to 6.5, we can see that the Lustris galaxies are not able to reproduce at all the starburst galaxies. So we conclude that for this finding, we conclude that maybe the simulation are not able to reproduce the starburst galaxies, and the starburst main sequence bimodality, perhaps because of a lack of theoretical prescription to describe, useful to describe starburst galaxies, or even because this kind of phenomena could happen at very small scale, even smaller than what we can probe with TNG 50, or maybe in the simulation, all those mechanisms that should suppress the star formation within galaxies are too efficient, like IGM feedback, stellar feedback, and so on. So that's it. This is the summary. So in this study, we found liminal emitter galaxies. We were able to trace star formation down to 10 to the 5.5 solar masses. We were able to trace star formation over 5 decades in stellar mass. Then combining blank no lensing field and cluster lensing fields, we were able, thanks to the Eiger statistic we had there, we were able to demonstrate that this starbus main sequence modality exists. It applies to all the whole redshift range we studied here. And it doesn't depend on which star formation ray tracer we decide to consider. Then we also estimated the fraction of main sequence and starbus galaxies, and we found a very high fraction of starbus galaxies, especially at redshift between 4 and 5. And moreover, we also found out that maybe the starbus galaxies could have played an important role in the cosmic star formation history in all the redshift we considered. And finally, we compared our observation with simulation, and we found out that maybe the current simulation are not able to reproduce starbus phenomenon at all. And so what's next? As an associate of the Media European Consortium in the high redshift group, we want to unfold the universe. In this case, we want to study the star formation ray stellar mass plane with the JWST data to confirm our finding. And here I wanted to show you the power that we can expect from JWST. On the right side, you can see the comparison between the same star observed by Spitzer and JWST. As you can see, for the JWST case, we are even capable of catch star galaxies behind this star. On the left, I show you the comparison in terms of resolution between among the infrared space telescopes. And as you can see on the right side of this image, MIRI, which is an instrument on JWST, is able to resolve everything there if compared to Spitzer and Weiss. And last but not least, there is also NIRCA, where I'm much involved. And basically, the filters we are able to use with NIRCA, we will be able to study galaxies up to redshift 12, 13, and so that's it.
Thanks. Questions for the speaker?
We have to stop the recording for the question. It's fine.
No, we are
Okay, people know that if they
yes.
ask a question, it will be recorded. Okay.
From home, from remote, or
Yeah.
Speak up.
Do you have some results or also about how the star formation ray density is distributed among galaxies of different masses? For example, trends with redshift.
No, we didn't check this. We didn't check this trend here, but we can do that later.
I have a question.
Yeah.
Do you have any clue about the metallicities of these starbus galaxies, and in particular, if there is a difference between starbus and main sequence?
Yeah, we noticed that for the starbus galaxies, there is a sort of trend where they prefer during the SED fitting the lower metallicity. In this case, for the SED fitting, we adopted the solar metallicity and subsolar metallicity. So we noticed that for starbus galaxies, there is a sort of preference for the subsolar metallicity. And
will you get more precise information with the data? For instance,
yeah, exactly. Because we will have much coverage at the Huygens wavelength, so we can constrain better also the metallicity, also the stellar mass, because for our study we estimated we performed the SED fitting based on 7 HST bands, and for the SMAPS galaxies the SED fitting is based on maybe 20 filters, but up to 3.6 micron with Spitzer. So with JWST, we will be able to constrain the stellar mass and to see if this bimodality exists, even if we are able to constrain better the stellar mass.
There's a remote question by Group Piori.
Hi, thank you for the very interesting talk. I have a question and a comment. The question is regarding the star formation rate density. Could you comment on your last data point, the drop that we noticed, that it seems that is almost flat, the star formation rate density, similar to what we find in the infrared, and then you have a drop. Could it be due to something related to incompleteness in the last redshift bin, or
Yeah,
can it be?
We thought that maybe this drop could be due to the fact that in the highest redshift bin we do not have the same statistics we have in the first two ones. So yeah, it's probably the thing.
So it's similar to what we found with Herschel. This green triangles at redshift 3.5 was the same thing. So it should have been an arrow going up.
Yeah.
And the comment is that what you find regarding the models, the galaxy evolution models, is in a sense similar to what we found with Herschel, that models were not able to reproduce the bright end of the far infrared luminosity function. So probably the brightest galaxies in infrared are also your starbursts. So yeah, I think is a similar result that goes in the same direction, that models, the current models, are not able to reproduce very luminous or star forming objects at high redshifts. So thank you.
I don't see any other question.
From home, questions? Don't see hands up.
Okay, so I think that's it.
Let's
Thanks
thank
again.
Thank you.
Questo fa